So, hello everyone. Who knows what's on this slide? RAM, memory, chips? Yeah, indeed, it's all kinds of chips. So there are many chips that we use. Memory, storage chips, processing chips, sensors, and things like that. So my name is Johan Janssen. I work at a company which is called ASML. Anyone an idea what ASML is? See one hand. So it's probably one of the companies that you never heard of, but whose end products everyone uses actually. Because we create the machines which all the major chip manufacturers like Intel and Samsung and TSMC, who created chips for example, Apple, they use our machines to create the chips you are using in your laptop and phones. So I joined this company about 2 years ago, and I learned quite a bit on how these chips are created, and I found it quite interesting because I realized myself, like, I've been using these for like 40 years, but never really had an idea how they are created. So I thought it would maybe be also interesting to share that knowledge. So that's why this session, basically, where we will look at how these chips are physically created and what the role of Java is in that process. So yeah, the amount of chips is basically, it's huge and it's only increasing. I mean, nowadays you have smart fridges, smart microwaves, which you can heat up stuff if you're driving home and things like that. It's getting more and more usage. And they even say we go to like 41 devices per person. I hope devices will become a lot smaller as well, because else it will be heavy to carry everything. Anyone an idea what this is? A wafer, indeed. And what's on the wafer? The Duke, the Java mascot, indeed. So this is a wafer. This is the basis for chips, basically. On top of this, chips will be created. And on this wafer, I put 564 Dukes. If you don't believe me, you can count them. This is about the amount of chips that are on one wafer. It can differ. I mean, like processor chips are often a bit bigger. Sensors are a bit smaller, so it can be a bit more or less than that. But this is a ballpark figure. In reality, they're actually printed across the edges. I put them nicely within because I wasn't aware of that yet. I learned later that they are actually printed across the edges as well. So the ones on the edges, yeah, they of course won't work because it's only like half a chip. And then on these chips, we create so-called transistors. So in the past, these transistors, you could still view them, photograph them, and basically they have like 3 connections, a drain, a gate, and a source. And it's a bit like a water tap. So water flows in, and then you can control what goes out. The transistor works the same, but not with water. They can't really handle that, but with electricity. And then you have Moore's law, which there are different explanations of how it works. I would say the simplest one is that the amount of transistors on a chip doubles every 2 years, which is quite insane, right? If you look at it, which other field do we know where stuff doubles every 2 years? Cars aren't getting twice as fast every 2 years. Buildings aren't getting twice as tall every 2 years. But somehow with chips we already do that for like 50 years, which is almost insane that we keep on pushing those boundaries and keep that progress there. So I put in some numbers here. In our world, we talk about nanometers and even smaller than that. So a nanometer is actually, or 1 million nanometers is 1 millimeter, so super small. So I put in some numbers here on how big some things are. How big do you think the transistors are nowadays that we print? So you saw one that we could still picture, but how big are the current ones? Any idea? 5, 4, yeah, around that area indeed, so somewhere below 10 nanometers indeed. So that's the sizes that we're talking about, and on accuracy we will see later it's even smaller than that. So we really approach like atom sizes for these kind of technologies. Why do we want to have more transistors? This is a book called Lord of the Rings. Maybe you read it, or maybe you saw the new series of Amazon. Won't discuss that one, else we probably fill in the entire hour. It has about 1,100 pages. It's a really thick book, even though the sheets are quite thin, but it's 1,100 pages. If we would print that with 13 nanometer accuracy, we could print it on a slice of A4 paper, 2,625 times. That's how small we're currently printing. And by making those transistors smaller, the chips can contain, for example, more memory, or more compute power, but also they are more energy efficient if the transistors get smaller. It's of course cheaper to ship if you need, like, I don't know, 1 terabytes of memory. It's cheaper if all the modules are relatively big in the number of gigabytes they contain. So there are several reasons why we want to go smaller and smaller. And then it starts with this, silica sand. So silica sand is there in abundance. It's not like a rare earth metal. And silica sand is used to create the wafers. And if we ever run out of silica sands and you see excavators digging up golf courses, then you need to worry, because golf courses also have silica sand. And from that, the sand is heated really hot, and they sort of pull out these so-called ingots. That's why it has this weird shape. It's sort of molten sand, basically. And that's the basis for the wafer. So when we have this ingot, it's being sliced horizontally into wafers. And they look like this. So within our customers' machines and at our factories, we often use a FOUP, front opening universal pot, and it contains 25 wafers, and these are then transported from one machine to the other. It's not that people walk around with wafers in our factories. It's way too sensitive for that. So yeah, if you look at how fast stuff goes, we process about 300 wafers an hour in a machine, depending on the machine. If you have a new generation machine coming out, often that number is lower. And then we keep on improving it to increase the number of wafers we can handle per hour. And that's basically per hour we print 1 layer. And we will see later we will print many layers, up to 200 layers. So it's not that in 1 hour you have 330 wafers with functioning chips. You just have 1 layer, basically. So it can be up to 200 layers. Again, it depends on what type of chip. If it's memory or processing, it can be a bit lower. And yeah, we now reach like 140 million transistors per square millimeter, which, yeah, it sounds insane. So how does it work? It's a bit like 3D printing. You've probably seen some of these machines in the past. You print 1 layer, then you print a layer on top of it until you have the structure that you want. That's almost the same what we do with chips. We also create layers on top of each other. But then with a quite more accurate way than your average 3D printer. So let's imagine you drive across this road on top of this line, the yellow line. You drive it for 300 kilometers, then you turn back and you drive the same 300 kilometers back without deviating more than 2 millimeters in total. That's the accuracy what we are talking about in like real numbers instead of nanometers. So then a wafer comes in, and it's a series of machines that do the chip creation. So this is one of the first ones. Here a chemical coating will be put on top of the wafer. It's called photoresist. So you see it's all automated. The machine will just pick it up, handle it, bring it back. And then it comes into this machine. This is a lithography machine. They're quite big. Nowadays, the new machines are 14 meters wide, 4 meters high, and 4 meters deep. It requires 20 trucks and 3 Boeing 747s to just ship 1 machine. And basically, with each generation, they will increase, as we will later also see. So this is the machine where the printing of the layers will happen. So the wafer with the coating on it, the chemical, is put on a magnetically levitating wafer table. So we cannot clamp it or something like that, because if we clamp it, it will bend and you will get more defect chips. So it's sort of hovering on top of this. And then what happens is we send EUV light to print the details in that chemical layer. And the next film will show you how that works. laser working. And actually, the big machine that you saw, the laser wasn't even in the picture, it's in the basement. Only the laser has 450,000 components. It amplifies the laser beam to 40 kilowatts. Then that laser beam will travel for 30 meters in the different machines. And then molten droplets of tin are being emitted at 70 meters per second. And that laser hits that molten droplet of tin. So first it hits it a bit soft, so it flattens like a pancake. Then it hits it hard. And then that tin will emit plasma, which results in EUV light. And that EUV light we use in our latest machines basically to shine on top of the photoresist chemical coating on top of the wafer. So that's basically what you just saw. And this is a recording of it. It's not a UFO, it's basically tin being hit twice and then emitting the EUV light. It's quite crazy, right? If you imagine that something is traveling with 70 meters per second and it's hit 50,000 times a second, or actually 100,000 times a second, because it's being hit twice without tin splattering around the machine. And there is another challenge there, is it gets extremely hot. The plasma is more or less comparable to the temperature of the surface of the sun. So gases are used to cool down the temperature in between of those 100,000 times that we shoot at it. So it's quite a miracle that the machine actually manages to do this once, but it's actually doing this 24 hours a day, the entire year. And within that, so we have that plasma emitting EUV light. We somehow need to get that EUV light on top of that resist. And for that, mirrors are used, but it's not like the mirrors you have at home. This is a mirror that has about 100 layers of special coating. And if you would extend it to the size of Germany, the biggest bump is 1 millimeter. It's super flat, so that most of the EUV light will end up on top of the wafer. Because EUV light, it quickly disappears. So everything that's in its way, make sure it disappears, and we don't want that. And then it goes through the machine. So at the bottom, basically, here the traveling begins. You see the EUV light going through several mirrors, up and down. And then here, this is what we call a reticle. We will look at that in a second. And then it goes further up and down until it's on top of the wafer. So what's that reticle? It's a bit like a stencil. You probably, when you were a kid, have used this to draw some letters or something on a piece of paper. The parts that are open you could draw in, and the rest you can't draw because it's covered. It's the same for a reticle. It has the pattern of one layer of a chip on it, and on some parts the light can shine through the EUV light, and on other parts it can't shine through. And then you have a reticle that looks like this. It's a bit more expensive than the templates that you used at home. One of these reticles costs about $250,000. So then that reticle is actually moving in the opposite direction of the wafer. So that wafer table is moving like this, and then the reticle is moving like this. So they go like this, and then they print with one in 15 Gs, the other one 5 Gs, and still it's continuously being checked and repositioned. So 20,000 times a second, they look, okay, how is the wafer positioned? Do we need to adjust it? And adjustments are even smaller than nanometer size. It's really small. And so the pattern of the reticle is 4 times as big as the pattern that will be printed on the wafer. The reason is that it's cheaper to build reticles that are not that detailed. And by using the mirrors and everything, we shrink that pattern, basically. And then it looks like this. So this is the reticle basically working with the EUV light going through. Now when you look at the entire machine, so at the right, it's currently being printed, the pattern. On the left, they adjust the wafer to the correct position. So before we print on it, we first make sure that the wafer is positioned correctly. And we do that in parallel, basically, to be able to process more wafers in the same time. But even if it's being printed, while being printed, it's also still adjusted how the wafer is laying on that wafer stage. And then in total, it looks like this. So at the top, you see the different reticles being changed. And at the bottom, you see wafers coming in, being measured, and then being switched to the part where they're printed on. So we briefly covered it already, but this is like a diagram of how it works. So we have that wafer, we put photoresist on top of it. Then basically the reticle is in between. We see the EUV light going through certain parts of the reticle, and then it covers here in the photoresist chemical coating. And then we can decide to either keep the parts where the light has shown on, or we can remove those parts. Some processes require one option, other processes require the other option. And we call that positive or negative photoresist. And this is then the complete picture. So I showed several parts. I showed, for example, the photoresist coating. We saw that in the beginning. So this part. Exposure, so that's the printing part. But after that, we will do development, baking, removing of chemicals and things like that. So it's an entire process, and this can take quite a while. And this happens for every layer. So if you have 200 layers, this circle is being executed 200 times, basically. And it's different machines from different companies. That's also interesting. So we make the machine that does the printing. We also have some metrology and inspection machines, which we will have a look at later. But for example, the developing and baking, the photoresist coating, and things like that, it's machines from different companies. So it's like an entire set of machines, one after the other, which work together to create the chips you're using. And then a bit about what state we're currently in. So nowadays, the advanced machines, they use EUV technology, which I just explained. The bit older machines, they use DUV. So the biggest difference between those generations of machines is how small of detail it can be printed. So each new machine can print smaller detail, and for example with DUV, here you see that something requires several layers to add some feature. With EUV we can actually print that feature in one layer. So that's of course quicker, than you only need to do that layer once instead of multiple times. And the interesting thing is, we sell these machines for about more than 30 years. And for the last 30 years, the machines that have been sold, 95% of these machines is still running. Of course, we do maintenance, replace parts and everything, improve them, but they're still being used. Because actually, like sensors, they don't require that really small detail. On the other hand, if you have really advanced chips in your phones or in your laptop, you need these really advanced machines. But still, only for certain layers. For example, the transistors, you want to have as small as possible. But we also have connecting layers, and there it doesn't matter if it's a bit bigger printed. So we can use some layers, the new machines, and for other layers we can use the old machines and combine them basically. And one of the advantages of using those older machines is often that they're cheaper, and they can process more wafers an hour. So they mix it in the companies, the usage. And then you get wafers like this. So this is real chips basically that are printed. And here you can see it's going to the edges. So these ones are basically worthless at the edges because it's only like half a chip. And then if you look a bit at the road ahead, so what's coming in the future, where are we going to? Often people ask like, hey, how far can we go? Can we even go further? Because we are reaching atom sizes. How long until Moore's law is no longer valid? And actually we are already busy with the next generation. The high-NA machine, so it's basically a next generation EUV machine. Already the first one was shipped to Intel, but it takes some time before our customers can use them. They need to create maybe new reticles, new processes to deal with these new machines. But in the next couple of years you can expect chips based on these new machines. And with even more transistors and more power, of course. So what's that NA that's being talked about? If we look at some of the older generations of machines in the past, basically we used this. So here you see light, you see a lens, there was air in between, and then a wafer. But because there was air in between, we saw quite some deflections of the light, which isn't really desired. We want to concentrate the light bundle. So then they found out if we put water in between, then basically focuses the light better, and we get better results. And that focusing, that's basically the NA we're talking about. So this water we already do for a long time is just to explain what that high NA means. So what will we get for other changes with high NA? So I already talked about the mirrors that we used in the old generation of machines. As you can read here, the new ones are even more flat. And maybe it's crazy, right? We print smaller and smaller details, but our machines are actually getting bigger and bigger to realize that. To give an example, the old mirrors, they weigh 123 kilos each. The new ones weigh over 1,000 kilograms. And that's from one generation of machine to the next. It's not 30 years in between, it's just one generation. So the sizes of the parts and the sizes of the entire machine, it gets really bigger and bigger. And something else which is happening is that it's way faster. So that reticle which is moving in the new machine, it can move at 32 Gs. And then you can see the old and the new one. It's basically, the new one is faster. And this is another video of it. At first I thought it was one of those funny YouTube videos where at the end the machine would explode. But apparently they managed to keep this going indefinitely almost at this speed. And one thing that's also more and more important if we reach those physical boundaries is that we need more and more measurements to see what's going wrong and where can we improve to make more and more better chips. So that's what we strive for. Our customers want to have as many wafers an hour and as many functioning chips on each wafer. That's one of the things that we are asked to do. And we take a lot of precautions for that. For example, we have really clean rooms in our factory, but also at our customer site. You see here, it's 10 particles per cubic meter. If you compare that to some people in America, they're quite dirty, right? But they probably don't need it. So for us, it's really, if there are really small particles in the machine, that could already result in chips not functioning. So it needs to be really clean. And it's even that extreme that if you work in these kinds of factories, you cannot wear perfume. Because even the perfume particles will influence the process. That's the sizes we're talking about. So actually, us humans are the biggest contaminations in these kind of rooms. They have special airflows and everything, but still, they measure how many particles are in that room, and as soon as a human enters, the number of particles goes up. So it's best if humans aren't involved too much. But still, some things might go wrong. So let's see if we print 2 layers on top of each other. We begin with the first layer, and then we print the second layer on top of it. It deviates a little bit. It's not really what we want, but still okay-ish. But if you do that too long, you can get to something which is called fallover. So basically, each line is shifted a little bit until everything falls over, and basically you have a broken chip. You could also print the layers next to each other. Of course, also not really helpful. Or you could even short-circuit them. So there are a lot of issues that might go wrong. And it's not per se that if there is an issue that you need to throw away the chip. For example, if you have memory chips of 32 gigabytes and we detect that there is an issue in some part of the chip, our customers can disable that part and sell the 32 gigabyte chip as a 16 gigabyte chip, for example, depending on how they designed their chip. So in the past, you also had these Celeron processors from Intel. They also disabled some of the cores of a normal Pentium processor and then sold them a bit cheaper. Of course, still our customers want to have those as few as possible. They want to have the good chips, and they try to prevent things like this. And you have sort of 2 approaches there that can go wrong. One is if there is like a dust particle on top of the wafer, then maybe one chip is incorrect. But if that same dust particle is on the reticle, then each wafer that goes through is basically affected by that dust particle. So it's way worse. So we try to analyze the results, how well those layers are positioned, how well everything is printed. And we talk then about 2 things. One is critical dimension, so how does the pattern look for one layer? And we look at overlay, so what we saw before, are the layers nicely on top of each other, or do they deviate a bit? And for that, we have 2 different types of machines, optics-based and an electrons machine, because you cannot really look with a microscope. It's way too small to detect issues with something like that. So we have special machines for it, so let's have a look at that. So here you see the FOUP with a number of wafers in it, and they're being analyzed. And what you see here is that we use different colors of light, and we look at the diffraction of the light to see if the layers of the chip are nicely printed with all kinds of advanced algorithms. So that's how one of the ways how we can measure if the stuff is going well, or if we need to recalibrate the machine or clean something or things like that. And so already we saw that wafer stage with the wafer, it was being adjusted like 20,000 times a second. But everything else, it's also measured, like temperature of the laser, all kinds of data. So that results in 31 terabyte of data per week per machine. So customers can have many machines, but this is just for one machine. And then we use that data, we do calculations on top of it to determine what went wrong. Maybe one of the mirrors was slightly off, or the temperature of the laser was slowly going up, and we need to put more gases in it to reduce the temperature. Can be almost anything. And that's how we basically recalibrate the machines. And here is one of the examples. So this, they call it a mirror. I found it a bit of a funny mirror because it's actually more than 4,000 mirrors which can be individually adjusted to reflect the light in the position that we want to. So we could actually change one of those or multiple of those depending on the measurements that we get. And yeah, this is one of the examples that we can control. So all that data basically goes from the different machines that we have. So this is where the stuff is being printed, which we saw before. All the data goes in, and then corrections are being sent back. But also the metrology, so the measurement, which we saw with the different colors of light, they send all the data to this platform. So we have a huge platform where all the data is going in. And in the past, basically, there were different applications that used that data. Each department created their own application, and those were used at our customer site. That was quite annoying because you couldn't really share the data across those different applications. The applications were relatively slow, and they had a different look and feel. So it wasn't really nicely set up. So after that, we started building a new platform, which we will see in a second. And that platform also runs on customer side. It's not something we can access. Customers are really sensitive about the data these machines generate, because based on the data they can improve. So if competition gets hand on those data, they could improve as well. So they won't allow any access. They don't run stuff in the cloud. It's all on-premise, completely secure. If we want to view a log file of our own application, we need to request permissions, and even then it cannot contain any sensitive data. And it's sort of the same for us, because we have all kinds of proprietary algorithms running in the application, and we also don't want the rest of the world to use them, because we have some competition that also creates tools like this. So we created this new platform, and it's basically so to analyze all that data. And we can do anything with it, as we will see in a second, but it's for all kinds of different departments. So some, they simply analyze some plain text data, but others, they maybe create pictures or whatever. And it all needs to go through the same platform, through one UI, basically. So on one part, it's really generic, and then on the other side, it's super customizable. A bit like a train platform. You can have fast trains, slow trains. Mostly, they use the same platform, and we need to support that as well. So how does it work? A bit more the technical, more Java-related stuff. So we use Apache Spark. Anyone using Apache Spark? No? So Apache Spark is basically a way to parallelize the work. So you can run Spark on multiple machines, and we call those the worker nodes. And then you have one sort of managing that. It's the driver and the cluster manager. So if work comes in, it's being distributed across those worker nodes to parallelize the work. And in the end, the result is brought back to the driver. So it's a way to highly parallelize things if you have either algorithms that are quite complicated or a lot of data, or a combination of those two. Then Apache Spark is really nice to work with. And on top of that, we built 3 types of plugins, or actually plugin development teams build them. We build the platform, and all the departments can build plugins. So we have UI plugins, basically to show different diagrams, or whatever they want to show, tables, pictures, whatever. Then we have data plugins to import the data into the platform, and we have processing plugins, which are triggered from the UI. So in the UI, you can select which data you want to analyze, and then you can say, okay, I want to run this algorithm on that data, and that algorithm is executed as part of the processing plugin. A bit bigger look is like this, with all the different things we use on top of it. So we use Spring Boot on top of it. We have a React front end, but we are also prepared to work without a front end, with just automatically executing jobs that are either triggered on time-based, or after X amount of wafers are processed, they automatically can use our platform. We use different data stores like MongoDB, Neo4j. So it's quite a big ecosystem of stuff that we're using. This is not the complete set, but I would say the most interesting parts that we are currently using. I guess a lot of them are familiar. And One thing that I always, you have these talks of Netflix and other cool companies that build really cool solutions. And then smaller companies try to build solutions using the same tool stack. I don't advise that. If something of this interests you, just pick one or two and try them. When we started, we didn't use Kafka for asynchronous messaging. We just used REST. And for the first versions, it worked perfectly. After a while, we realized, okay, we want to be a bit more reliable, so we switched to Kafka for asynchronous messaging. But that's the way we gradually improved. We didn't start with this stack from the beginning. We just kept on adding things whenever we needed them. So our main platform is built in Java, and plugins are built also in Java, but they can actually use different programming languages as well. So for example, a lot of our departments, they have people with a physics background or mathematics background. They're not per se Java developers, and they already have a lot of algorithms coded in different languages, so often a bit more lower level languages like Julia or C or MATLAB or languages like that. And we also want to accommodate those algorithms so that they don't need to rewrite them in Java and need to maintain two sets of algorithms, because some of those algorithms are used both in the machine and in our platform, and you don't want to have two versions that you need to keep in sync. So basically, we offer different possibilities to integrate these languages, for example, via JNI or by executing them remotely in Docker containers and then sending events back to the platform and exchanging data between the platform and those Docker containers. And in the Docker container, you can run basically whatever language you want to. So nowadays, AI is super hip, so every talk needs something from AI, right? And I actually found that we have a quite useful case of AI in one of the things that we are doing. So as I said, we want to scan our wafers to see if something is defect, and if that's the case, we recalibrate our machine. But that scanning takes quite a while. It's basically a bottleneck. Printing is faster than scanning, so the more you scan, the more it becomes a bottleneck, basically. So we want to scan as fast as possible. So at the top, you see a fast scan, basically, and it captured almost 70% of the issues. If we slow that scan down by 8 times, we capture 100% of the defects. But that probably means we also need to scan 8 times as less wafers, because we don't want it to become a bottleneck. And then we might miss stuff again, which is also not really desirable. So my colleagues actually used deep learning to improve these images. And with that, they could capture almost 93% of the defects, while still being like 8 times as fast as this one. So that's, I think, a nice improvement based on AI, deep learning. And within our platform, basically, we try to make things as easy as possible for the plugin developers. As I mentioned, they sometimes have a different background, programming background, educational background. So we created Maven archetypes, documentation, and everything, so to make it as easy as possible for them to get started. And to give you a bit of an idea on the size of this project, currently on the platform side, there are about 150 people involved, including management and everything. It's not pure developers, but it's several teams. And that's excluding the plugin development teams. That's even way more teams. So it's a relatively big project. And then what comes out is this. And probably, like me, when you first look at it, you have no clue. Just some diagrams, right? So let's see if I can explain some things. So for example, here at the top, we see that the TDBB was executed, and that's actually one of the algorithms in the processing plugin. And that resulted in, for example, this. It's called CE, as you can see at the top. It's correctable errors. And what we see is that all arrows point in the same direction, which basically means, for example, if you have 2 layers on top of each other, it's like this. They are a bit wrongly aligned. So in the next step, maybe we can do it a little bit different and print it like this. That's correctable. We know how we can fix it. Then on the left, here we see non-correctable errors. They point in all kinds of directions. They also have different colors because they're bigger or smaller. For those, we don't know how to correct it. I mean, if one arrow points like this and the other points like that, if we corrected that side, this will be even worse. So we don't really know how to fix that. We could, for example, use even more advanced algorithms and maybe distill some correctable errors out of that one again. And we have some colleagues who sometimes even can see improvements based on their own experience on top of this. So this is one of the ways how we can visualize and analyze the data that we get from the machines to recalibrate them. So a bit to recap, you often hear that Java is old, Java is slow and not really relevant anymore. This is a new platform which was created like 3-4 years ago, and they explicitly chose to build it in Java. While it needs to process large amounts of data and has really complicated algorithms. So I think Java is still really relevant. And for me, one of the reasons is because of the ecosystem. You have a lot of developers who are familiar with it, but also a lot of tooling. If we run into something that we want, there's often a tool that can help us with it, or at least partly help with it. For example, we use Apache Spark to parallelize all the work, but Apache Spark didn't show any progress, so our user couldn't see how far the algorithm was. And while some of our algorithms execute in seconds, we also have algorithms that take hours to process. And if the user doesn't get any feedback, they're like, hey, something broken, or is it still processing? So we actually built like a progress monitoring solution on top of Apache Spark to give some progress back to the user in terms which they understand, because the progress in Spark uses Spark concepts, and our users don't know Spark. So that's how we gradually kept improving, and we're still improving. I think it will continue indefinitely. There are always things to add. So that was like the quick introduction to chips. Any questions? Everyone still awake? Yeah.
Rectangle. Because
it's a good question. So why are wafers round and not rectangle?
the chip is rectangle.
The chip is rectangle, indeed.
Maybe you can cut the losses on the edges.
I think it has to do shortly with the printing, and also probably if something is a square, it's more brittle. The edges could break and things like that. So they actually did a lot of tests. Also for wafers, if you look at the history, they started with, I think, 10 or 15 centimeter wafers in diameter. Now most use 30 centimeters, but there are even some that are bigger. But they found out that the bigger ones, it was less economical, and because they're bigger, they tend to bend easier, which results in not as many good functioning chips. So they actually did quite some research, but it is indeed weird, because if you would have square ones, you could nicely print the chips on it instead of having the waste around the edges. But probably really smart people found out that a round one was better than a square one.
Yes.
Good question.
As a no, not in it. Okay. I think it has to do with the tension. It's the same reason why the windows on the plane are not square and they're round, because they have a lot of tension in the corners.
Yeah.
And they tend to bend yeah.
Yeah, that's a good one. Yeah. Okay. Any other question? Then thank you all and enjoy the rest of the conference.